Talking about mechanics on bacteria and bacterial cells, uh, and whatever this on the surface of the bacterial cells, the flagella and microvilli. In general, today this lecture I'm going to speak about what are the new developments in cell mechanics using AFM, and these developments are not really in terms of the protocol of measurement. The protocol remains the same, doesn't change, but the analysis methods now, people have used different ways of making sense of the same data uh, by paying attention to all the details, and this is what I will focus on mainly in this lecture. Okay, so uh, cells are complex materials, and typically cells are also called, falls in the category of something called complex fluids, and complex fluids or solids have a response that is not something similar to materials that we are used to. We are actually used to lot of different kind of materials, but in textbook up to 12th standard we always understand everything around us and its mechanical response in terms of either Hooke's law or a Newton's viscosity, right? And this means that we have a clear idea about when something is purely a solid in terms of mechanical response, how do you sort of describe them, and when it is purely a liquid like water, or even denser liquids like even honey for that matter, where the viscosity is large, and we sort of know how do we sort of put that response into a formal equation. In case of solids, we always have a Hooke's law, and this was you apply force to spring, and this application of force at time t equal to 0 instantaneously causes a elongation of the spring. For instance, if you attach a take a wire and attach a weight to it, moment you attach the weight to it, there is a full elongation of the wire, and this essentially one can then look at the cross sectional area of the wire, and you divide the weight by the cross sectional area, you get a stress, and the elongation of wire per unit the length or whatever the percentage elongation, which is called strain. And we always know that the stress and strain are proportional to each other, and the proportionality is basically the modulus of elasticity, or Young's modulus as we call it. And many times you will see, even in the previous talk, we report Young's modulus of material to sort of characterize it in terms of is it soft or is it stiff. Okay. So, high Young's modulus means very small elongation of the wire for a given force or given stress. So if the material is stiff, the Young's modulus is high. If the material is soft, then Young's modulus is low. So this is how we look at soft and stiff materials, as long as they are all solids and as long as their behavior follows this particular thing, that the stress upon strain is proportional to strain, and there is no time involved in all of this. You apply a stress, you get and that very moment you get the full strain in the material. So these are solids. Then we have something called Newtonian liquids, and Newtonian is important here because this really follows, just like the two ways to say this, whatever I just said are also called as Hookean solids because it follows Hooke's law. And then we also call Newtonian liquids, which means it follows Newton's constitutive equation. It is not the standard Newton's law of motion or gravity. This is a specific equation that Newton came up with that describes the response of liquids to external forces. Okay. Now, it is common knowledge, or you must have experienced this also, that if I take a stick and put it in water and stir it, clearly when I do it fast as opposed to I do it slow, the force I feel in my arm is different, the resistance to your movement. And this force is actually a kind of viscous stress that is developed in liquid, is giving you, or your arm is measuring it in a way that its force is large and so on. So this viscous stress now clearly depends on how fast and slow you are doing this thing, right? Which is not the case for solids. There was no time. You apply a force to the wire slowly or fast, or you apply a force and after some time the elongation happened. There was no time involved in all of that in when you start up looking at Hookean solids. Whereas if you do a liquid, faster you do it, more the force, okay, more the force, viscous stress that is developed. Now, the viscous stress developed in a liquid when it's subjected to strains does not depend on strain, but depends on a strain rate, right. So, if I got oscillatory strain, which is say going as some strain, peak strain value multiplied by sin omega t, that is the description of oscillatory strain in the material. The viscous stress developed will go as cos omega t, and this is you also can roughly feel this, right. You would do shaking the thing in water, the maximum force you feel it is not when you are turning back, but when you are in the middle where the speed is highest, right. You are shaking this and you go at the end, the force you feel is lowest because it's coming to rest almost momentarily, and then coming in the middle you are really doing this fast, so that the resistance you feel is fast. So clearly when the strain is close to 0, the stress is maximum. So it is 90-degree out of phase in a way. So though this is fine, and normally if you think about states of matter, when you say solid, liquid, gases, this is just a classification scheme and it's never complete. Okay, I say solid, liquid, gas, and this is not the full thing. It's almost like taxonomy in biology. Then in liquids you will have further descriptions. There will be gel, there will be glass, there will be a lot of things. If you get to go to liquids, there will be things like like superconductivity, on all of these things also treated like flow and liquid. So it's never complete. Our focus right now is on this thing, that in terms of mechanical response, you got a liquid like response or a solid like response. Okay, that's the first thing that we have to keep in mind. Now, what are cells? The question is it Hookean solid? And all the papers you will see on cell mechanics will typically sort of report this number, the Young's modulus of a cell. And this is where you have to keep in mind that this statement comes with very basic assumption that I am calling this as a Hookean solid, and that's what my assumption is. And how valid that assumption is also you can question. Because cells, if I put them on a surface, they are not going to have their own shape as we learn it in class, right. The solids have their own shape. The moment you put on surface, it will spread a little. If you do polylysin treatment, it is like a round thing without spreading too much. So all of this indicates that the cells clearly are not Hookean solids. They are not steel rod, for instance. Okay, and most of the biomaterials are not Hookean solids. Even if you things which are devoid of water, silk thread, for instance. If I apply weight to a silk thread, the response to the weight is immediate, yes, to some extent, and then there is something called creep, which means that if you keep the stress same, and the silk thread will keep elongating little further, and the time required to attain and then it will stop elongation any further. So the time required to attain full elongation is something called creep relaxation in materials. So silk clearly is not Hookean solid. Okay, so most biomaterials, yeah.
Creep will be there even for Hookean solid also. I mean, beyond this
Hooke's limit, yeah, beyond Hooke's limit, but then it is again not a solid anymore. So if you load it beyond yield point, then the material flows anyways. This Hookean solid is idea only works till the point where you are perturbing the mean position of constituent parts like atoms to some and when the constituent part starts to flow with respect to each other, this is not it's not solid anymore.
So for silk worm, this thread,
Yeah.
this is not like, even for small deformation it is not clear.
Yes, even if we attach a small amount of it, the thing is not instantaneous. We will get a creep and then it's complete, and there's no flow really in a way. It's all entropic in some sense. So there's no flow. Like solids will be the yield, after yield point there's a flow and there's a creep, and that particular region we never call within a Hooke's law, right? This is the point. Okay, so you got this idea that this is what happens. Now, how do I then characterize material, and how do I classify what is the classification scheme now between liquid and solid? We got something in between now, because partly you have an instantaneous response of this, let's say, silk thread. So that is a Hookean response, and then it starts to extend further, and this takes own time, and if you take different type of material that will again expand like that, that time will be different. So now to attain full extension, there is a time factor involved, and that time factor decides really how much sort of liquid like the material is and how much solid like the material is. So at beginning one can say that the cells are viscoelastic. They are a viscous part and elastic part. Okay, and why do we say that? We will come to it a little later. And now the idea is, if I push the classification scheme little further, within viscoelastic materials you have lot of them. You got soft solids which are described by standard linear solids equation, then you have gels, then you have glasses, and you got lot of this thing, and each one of them is mechanical response can actually be characterized pretty well through rheology, and we can classify this scheme in this way. Now the question then is, where do cells lie in all of this classification scheme? And that's we probably look at it. So the way, I mean, it's pretty simple for application of force to a steel rod, and you sort of measure length, elongation produced. There is a simple kind of laboratory experiment in a first year of physics lab, or 11th, 12th even, your school. But that is not the case with cells. So cells, if I want to characterize their mechanical response, this application of force has to be done in a very subtle way. And there are various ways of applying force to the cell. One of them is you take the cell, eat some magnetic kind of small nanoparticles, and you apply magnetic force. And then as a result, the magnetic force will deform the cell. Now the question is, what is the cross sectional area that you are, is just like, because it's important to get stress first, and independent measurement of stress and strain is a very important in something called rheology, which means this is a science of probing mechanical response of complex materials which are neither solid like nor liquid like. Okay, so and because everything depends on the constitutive relationship between stress and strain. For liquids, as I said, stress divided by strain rate. For solids, stress by strain. If I standard linear solids, it's different equation. For glasses, it's different equation. So everything is a relationship between stress and strain, and that's the constitutive equation of the material. Okay, so it's very important to measure stress accurately, independently, and strain also accurately and independently. Okay, and then you sort of get the full idea of what the mechanics of the system is. And this is purely a perspective of, let's say, physicists and chemical engineers and mechanical engineers. But then cells being complex objects, there, it's difficult to sort of say what is the, if I make them eat some beads and apply force, the stress is very hard to characterize. You can get some strain, but at the best what you can get is how long the cell took to respond. For instance, apply turn on the magnetic field, immediately some, just like a silk rod we said, something happens immediately and then creeps for a little and then stops. So at least you can look at the time response, and this time response can tell something how much solid like and how much liquid like the material is, but it still doesn't tell you which equation should I use now to sort of fit my data. Okay, so these are the problems. So the second thing we could do is put a if you gel particularly, that is fine, not on the cells. You make a steel ball sit on a gel material, and look at the time evolution, how it sinks slowly, and at one point it will stop sinking any further, and then you sort of estimate the contact area. So weight of the ball, the contact area, sort of gives you application of it gives you some idea of stress, and there are these famous equations in contact mechanics which can be used to get an idea about Young's modulus and other things about the cell. And this is coming very close to what AFM does. Okay, in AFM, or AFM does on cell. Okay, so in the typical AFM experiment, one could think about is that you take a, we now already know we have a tip, and then you press on a cell. But when you, with a sharp tip, you sort of press on a cell, are you pressing or you sort of poking is the question, and clearly you're poking, and this poking sort of gives you a different response than pressing fully, because poking might be a poking of a balloon filled with water. Okay, and then that poking probably only looking at the tension in the balloon rather than the mechanical properties of the water inside or the rubber itself. Okay, so this is where also one has to be careful while you do AFM experiments. You poking or are you really deforming the whole thing in global way? Okay, and then sometimes you have to attach a bead, and attachment of a bead is essentially, and then press down with the cantilever, and you know the known force you press down with, and that's similar to putting a steel ball on a material and look at the sinking, how it sinks and to what extent it sinks. So that's there are various ways of doing mechanics on the sail, but whatever it is, the yeah.
When you're saying poking and pressing, so are you talking about the force or the contact area?
Well, contact area is always important. No, contact area tells you the force by contact area is the stress that you are imposing on the material. So what I am saying is that so if I have a stretched balloon and I press on it with a finger, it always presses you back. Now, what is it that pressing you back? Is it the Young's modulus of the rubber of which the balloon is made, or it's the surface tension, like or a tension in the thing, like an inflated balloon and balloon that's not inflated. If you press on a balloon that's not inflated, clearly you are getting Young's modulus of the balloon material. But the inflated balloon, you are pressing on it, you are getting the tension that is there in the membrane like thing that you, and cells are similar. You poke, you probably will measure tension rather than Young's modulus. So one has to be careful there also what is it that one is measuring. Okay, yeah. So all right, so the point is no matter what you apply stress, measure strain. That's the stress strain analysis that you do. Now you apply stress in different ways, and this is what it will appear, and then this is very similar to, as I said, application of weight to the steel rod. You at say 5 seconds, you have applied a force, whatever way you applied it, and if it is solid, Hookean elastic solid, dt is that also time in there. In case your response, in particular in case of elastic solid, the response is instantaneous. So you might as well just put d by d max to get you full, and it's 1, the full elongation is occurred. And what happens for elastic solids, 5 seconds apply the stress, and then the whole thing is complete. At 15 seconds I remove the force, okay, I remove the stress that is imposed on the material, and instantaneously it recovers back fully. So two things: one, it's instantaneous; second, the recovery is complete. Okay, so if I pull on a spring and I release, spring will go back where it was before, and that's important for Hookean solids. If the same thing if I do for liquids, then clearly you apply sort of subject it to stress at this particular time, 5 seconds, and the strain is not instantaneous. It is sort of, and as I said, this is going to be the strain rate dependent, so it is going to be for a simple thing a straight line. And yeah, and then what, at 15 seconds I said, okay, I don't apply this stress anymore, but the deformation is fully plastic. Okay, it is flowed and it is there. So for instance, if I take something like a clay and deform it, and I take back the force, the clay doesn't come back, it remains the way it was. And this is what you mean by whatever deformation is produced, it's basically continued. And these two follow the constitutive equations, which is stress upon strain is the Young's modulus, and here the stress and strain will be eta, the viscosity, the proportionality constant, just like in case of solids, the proportionality constant between sigma and stress and the strain rate is viscosity. Okay, so that's for two extremes. Now and this extreme, the material that is taken for such a thing is PDMS, which is you can also take collagen which is not cross-linked well enough. You could take many gels which are not good cross-linked to an extent where the response is fully like liquid. Okay. So, this is the two extremes. Now, cells do something in between, and that's what most viscoelastic materials do also. Okay. And what do cells do? If you apply, again it's very similar to silk thread, we apply stress at 5 seconds, and now some part of it is instantaneous, as I said. You get the deformation to some level, and then it is sort of building up to get the full thing. And if you sort of it is already reached the full length, and if you keep doing this further, it will just remain flat. Okay, because it's now attained the full length of this thing. But then moment you sort of stop the stress, remove the force, then there is some instantaneous recovery, but the recovery is not complete. There will be some part that is again with time slowly recovering back, and it is never complete. So now part of the material which was elastic has recovered back, part which was not elastic and viscous has not recovered back, and the way this thing builds up, the time needed to build this up and time needed to come to whatever residual strain that the material is keeping, or plastic deformation one can say, that time evolution sort of is quite important. Okay. Now, the question here is this: the way the time evolution of deformation happens and the way it also decays down to residual strain, this nature of this is quite important. One could have a single exponent for both these, which means the materials have a characteristic relaxation time, we can say. And what is that relaxation? Characteristic creep relaxation, you can say, because that part is a creep in a way. So what one can do? One can come up with a constitutive equation just like this, okay, to describe this particular rise. And if it is Kelvin-Voigt kind of material, which means I can describe the material simply as elastic part and a viscous part. And I will say if they are arranged in parallel or in series, this spring and dashpot. Then if it is arranged in series, one calls it as a Maxwellian or a Maxwell's fluid. If you put them in series parallel, then they are called Kelvin-Voigt material. This beaded chalk. Okay. So, elastic solids, one can describe them as a spring, like we think about circuit elements, no, we say resistor, capacitor, inductance, all of this is described in such a way. So, this is a spring which is and you whatever the force and extension is proportional to each other, and also there is this dashpot to describe the viscous part in the material. Okay. If I put them in series, because I am saying now the combination of these two sort of gives you the total response, right, total thing about the material, then this is Maxwell. Between the two, I can also have a thing such as this. And this is Kelvin-Voigt. This is the simplest description I am still telling you. Okay. As you can see, we just sort of moved from just solid or just liquid. We have moved to a description where I am saying that the material is both elastic and viscous in nature, and I either put those two parts in parallel or series. Now you will say, what is the meaning of this? What is the point of putting them in parallel and series? Well, if you really think about it, this sort of approaches solid-like behavior, this approaches liquid-like behavior, because if I apply stress, if I apply force on this, then the creep is infinite, right? Because this deformation will keep on happening, and this is what, if we put it in this way, then this will always resist any further deformation. So, so it is not going to elongate forever. So, this is something that also we have to see what difference one is putting in mind. Now, these are these kind of materials, this Maxwell's thing, which is talked in terms of relaxation time. And that means if I apply a stress, release it, what is the time it takes for the stress to relax back? This is called retardation time. And retardation there means that this part, apply a stress and how long it takes to respond. And for Kelvin-Voigt or Maxwell, this kind of behavior will be single exponent. Okay, this one time scale only, characteristic time. These are called linear viscoelastic materials also. Okay, so that's the thing. Now you will say, yeah, fine, good. So the cell's perfect, right? Yeah. No, as you can see, this actually measured data. It's measured thing. It doesn't drop to 0. As you can see, the cell, the red part, it just continues to stay there. And even if you, stress is removed and it is fully almost gone back to what it wanted to go back to, but not to 0. It will just continue like that.
This is creepy compliance data.
Sorry?
Creepy compliance data.
This data is collected with which equipment? I think these are done with magnetic beads.
No, it's the inverse to the mean square
It's
displacement.
compliance. This is compliance. Yeah,
Yeah.
you can see. Yeah, this is compliance. You can J0 is the compliance.
It's the inverse of the mean square
It's a
displacement.
mean inverse of stiffness
Stiffness.
here. Yeah. So J of T is the compliance, not stiffness. As you can see, dt by F, not F by D. F by D would be stiffness, no? Force upon displacement. Cell as a whole. We are talking about cell as a whole. This is they make them eat the beads and the beads are all over, and then you are applying a force to the whole cell. No, this is a whole cell. So it's very difficult to separate it out. No, even suppose I make the one organelle of the cell to eat the just somehow theoretically or hypothetically manage to do that, and then you apply the force on it. It is still the application of force when the organelle is surrounded by the cell. Yeah. So what am I measuring? If it was just the outside organelle was outside without anything of the cellular milieu, then you could say it is just the response of that particular organelle. But if anything that you put inside and try to shake, the whole material is going to. That's like microrheology also is similar thing, that you look at the whole material. So it's very difficult to separate, saying that this is.
Characterize the viscoelastic nature of components.
Yes, this is what we'll come to. That's
Okay.
why we're talking about
Okay.
cell mechanics using AFM. All right, so this is a fantastic review by Kalmansberger and Fabry. They've done a very good job. Okay, so the thing is, now you said perfect. So cells are viscoelastic, and you got very nice, simple construct. All you have to do is get the one single relaxation time, and you are done. Characterize the cell fully, in a rheological way. But cells don't do that. Cells do not give you single exponent. Okay. There's also another thing which is similar to Kelvin-Voigt. It's called standard linear solids. It's just addition one more of spring, but let's not go into the details there. But that will give you a single relaxation on a lot of materials show that single relaxation. Cells actually show something that will be followed by this equation, and you can see there is, I don't know if it's fitted there or not, but the compliance, and there's a peak some J0 value. If there was no time part, is just d by F, that will be your J0. What it is saying is that with time it actually follows a power law, and there is this the exponent there. Okay, and again if I do this kind of thing, this also follows a power law. What does that mean? What is the meaning of power law? Like in terms of equation, yes, we have written it there. Power law in physics is a scale free behavior. Okay, so if I take any equation that has a power law of y as a function of x raised to 2 or x raised to 3 or whatever, and it is if you try to plot it, whatever part you zoom, it will look exactly similar. Okay, so in a way it's also self similar. If I take x square and I just zoom little part of it, it will look like if I am looking at the scale of 1 to 10 on x axis or looking at the scale of 1 to 0.1 on x axis, and if you just plot them, it will actually look exactly similar. You see my point? If I say take a y equal to x square and plot it from 1 to 10 and take it y equal to x square, plot it from 0.1 to 1 or 1 to whatever value, and these you keep the 1 to 10 and 1 to 0.1 scale as same, it will fall on each other. Okay, and that is basically a scale free behavior. So it doesn't matter what scale you are trying to look at, it will just be keep. Exponential on the other hand, e raised to x minus the one that is falling exponentially is not scale free. After decay, characteristic decay length, you don't just worry about it. We like the exponential distribution that Sabyasachi talked about yesterday, the average time, age or whatever, that survival probability turns out to be the decay length of the exponential part, and we don't worry about it. But power laws are not like that. They are scale free. Whatever scale you pick up, they will have the same behavior everywhere. And this can be also understood in terms of having infinite number of single exponents. Okay, which means it has all time scales. It's scale free. The behavior is same, or all time scale the behavior look like same. If I watch the thing for 1 to 10 seconds, if I watch the thing from 10 seconds to 100 seconds or a million seconds, it will look exactly same. Okay, and that's the nature of scale free. For instance, if I watch only this part and I watch only that part, and if I sort of put them on the scale, it will look same. That means it doesn't have one relaxation time, it has all relaxation times in terms of times. And this is the sense of that is something in power law. What does that mean? That means that, and this is also in a way good, cells do follow power law. That's one thing good. But what's also nice to sort of, it's kind of consistent with the picture that inside a cell, so many processes are happening, right? Myosin walking, this whatever kinesin is doing, whatever is doing, enzymes are turning over substrates, and it's an extremely dynamic process, and each one has its own time scale. And how many time scales are like that in there, who knows? It's such a complicated thing that they've got all time scales. So in a way, one can look at cells and say that, okay, there are so many time scales inside it, and you sort of are probing it globally, and as a effect it will give you a power law. So what's nice about it? What's nice about it is this, that suppose it was following only 3 time scales, which means I got 3 such things, 3 springs and 3 dashpots, and you combine them in a whatever way, and either parallel or series. And what does that give you? It will give you, each one of these will have 2 parameters, right? And that means 6 parameters. So 6 parameters, if you try to fit to a decay process with a 6 or 3 different time scales, each one has a prefactor and the time required to fall, power essentially, and the time required to fall. You will get 6 parameters to describe it. Any 6 parameters will be okay to give the description. Yeah, this is what the problem is. If you have more parameters to describe your system, you are in trouble. Any combination of these parameters will basically be able to show you the same behavior, and it's very difficult then to say anything meaningful. So if I model the cell as just something is a viscoelastic material with a couple of time scales, it's a problem. But if it is infinite number of time scales, then it's nice, because then it's a power law. And power law has only, as you see in that equation, just two parameters, J0 and beta. Okay, or tau and beta, not even J0. So just two parameters are required to fully describe the material. Is this instantaneous compliance or young elastic modulus, and the exponent which is giving you. Now, what is the meaning of this exponent now? The exponent is, and this is where a little bit of too much of mathematics, and I also don't understand fully, but it enters into something called fractional calculus. When we took stress proportional strain, I do not take a derivative, and let's say that's beta equal to 0, 0 at derivative, right? No derivative. But here stress proportional strain, I do first order derivative, and that's beta equal to 1. And when you have a power law kind of behavior, what happens is that the stress is proportional to strain rate, but the derivative is neither 0 nor 1. It's fractional. Okay, and this is a little difficult to get over with, but this is called something called fractional calculus. Calculus, the order of derivative is always 0, 1, 2, 3 like that, but in fractional calculus the order can be something between, and most of the fractals, most of these very exotic looking patterns will show you a fractional calculus follows a fractional calculus, for instance. But that's another topic. What it tells you that is the constitutive equation for a power law behavior is something like that, and if I have a beta that's going towards 0, I have a more solid like material. A beta that's going towards 1, I have a more liquid like material, and beta that is in between, suppose it's 0.9, I would say it is more liquid like, 0.2 is more solid like, and so on and so forth. And meaning that one can attach to beta is that its effective noise temperature. And also in classification of material schemes, the materials that follow power law in terms of relaxation, once you remove the stress, they relax, and if the relaxation is not single exponent but a power law, then you can say this clearly is a glass in physics. Okay, so all glassy phases like the glass that you see around is basically showing this kind of relaxation.
So this property is because of the lipid membrane? Just because of the lipid?
Property is basically because of infinitely large number of different processes happening at all time scales.
Okay. And
now the question is this, then that means that you got an energy landscape, let's say, and each one is sitting, someone is deeper, someone is not so deep. So myosin walking on a microtubule or whatever process is happening, that particular thing, if it's way too deep, it's kind of frozen. Now some process, so the whole thing, what we are saying is that if beta is solid like, then things are frozen, and beta is towards 1, things are mobile, and it's a soft glass as opposed to a normal glass that you see on a window pane.
So, but here we are measuring the whole cell and understanding how viscoelastic property of a cell is, and
Yes.
The thing is this property is not just because of the lipid but also the internal,
The whole thing, just not lipid, or just not one guy doing one of the enzyme is turning over substrate, that's doing fast, the other one is doing slow, third one is doing in between, a lot of things happening, and you don't care about what all. Just that if beta is too close to 0, the effective noise temperature of the system is gone down, and as a result things are frozen like the glass that you see on a window. But if I raise the temperature of such a thing, it will be a glass that is not so much frozen, and the effective noise temperature is now gone towards the value of beta equal
so
to 1.
it changes with temperature also.
Effective noise temperature, everything is happening at, is all fairly a non-equilibrium system. The glasses are fallen out of equilibrium things, and what we are saying is how deep are the pockets now in the energy landscape, so that they don't come out and mix with each other. And if they are deep enough, that means the effective noise temperature is lower. If If they're not so deep, then it's higher. But if you really measure temperature, it's just maybe body temperature, you know. So it's effective noise temperature, calls.
Okay, thanks.
And we'll come to we'll show you a result from our lab to just
How to estimate
from fitting. It's the power law exponent. If you take basically if you take that stress upon strain and log plot, you will get beta. Slope of that.
J0? How do you get J0 is a
This is instantaneous, or this is the peak modulus. Yeah, you can. Yeah, right. You can get from these two things. You can get J0 and the beta. Okay, there's no single time scale, so there's, and you have to make it dimensionless. So t by tau 0, you have to choose appropriate time scale to normalize and see the axis. Yeah, and in AFM experiments, it is the way to do that.
So there will be three parameters. Actually,
No, no.
it also
Yeah, but that is really if you change it by from 10 milliseconds to 1 millisecond, nothing changes really. So that is really a parameter that doesn't change anything. It's just a way to say, okay, fine, this is the time axis, to normalize the time axis. You know, normalize in sense, make it dimension free. This power law, you can't keep something. Yeah.
So what if the cell is fed? So then in what criteria we will fit the cell?
Dead cell. We haven't done it on a dead cell yet, but probably my thing is it will follow one of the single time scales. Maybe we should try this, Shubham. But that the dead cell will act like it's like a normal material. What I'm suggesting here is that because cells are a dynamic entity and the processes are happening all the time, they actually behave like glass. A dead cell probably will have a single time scale. That is, and then it is not so important.
Continuing the same question, do you have any idea how liposomes behave? Is it the same way?
Liposome as in?
Like phospholipids, liposomes?
Well,
Like
that's not such a complex object.
It's not, but
It probably will be some viscoelastic thing. As I said, if you take this, like a vesicles and which are empty vesicles, then you normally talk about the surface tension and do not talk about the Young's modulus of the membrane. It's a membrane limit.
okay.
You got the material in a membrane limit, and then in membrane limit typically surface tension dominates and not the material property, which is Young's modulus.
Okay.
Hi, so if you remove some components from the cells, will it still follow the power law? Like if you are comparing a nucleated and unnucleated cell.
I think so far what all the kinds of cell, including bacteria, probed with AFM and largely with AFM and this bead rheology thing, all of them follow power law.
Thank you.
So far. Beta? No. That's the whole game. If it is same for everything, no fun. Yes, it is different. And that's why it is interesting that it is a parameter that's sensitive to what type of cell it is. Now we'll go to results. I hope that when I say cells is a soft glass, I hope everyone got what I mean by that. Yeah.
What about the effect of probing itself? Like the AFM probe is applying some force. How is it changing the energy barriers of infinite processes that are happening? And it is that effect we are seeing. How do we ensure that?
That is
it
hard to
intrinsic
do.
or-
It's like putting a thermometer into a temperature bath, and what if that changes the temperature of the bath? So one can go by this, that our application of stress should be minimal, so that all the internal processes are not affected. If the application of stress itself kind of changes the exponent, it's likely that it happens. But we go with the assumption that if you press with a nanonewton force, and this is also we do make sure that do not exceed 1 nanonewton, and then going by the rough Young's modulus of the cell, how much you are perturbing the cell, and then you can translated that to the level of single molecule, maybe in 5 nanometer you are causing deformations of femtometers or angstroms, then you are okay. But yeah, one needs to estimate how much is it really, and we also see what that is the point. Yeah.
This curve is only based on mammalian cells and bacterial cells. Not our. How about plant cells? They have a rigid cell
Plant
wall.
cells, no, I don't know if anyone is probed so far, but bacterial cells people have probed. Different types of cell lines people have probed largely.
So those are only like mammalian cells and those which are
Yeah,
like
cancer
flexible.
cell lines
Yeah.
also. Yeah.
I think it will be interesting if you can see whether that
Bacteria have been probed like this. Yeah.
plant cells. If
Plant
you-
cells, I don't know if anyone has done it in my at least.
So this
knowledge.
model, whether it will fit or not, because they have that cell wall.
My
and-
guess is it should, because it's
Okay.
again a similar thing in a way. Dynamic process of all time scales involved in plant cells also.
There is cell wall that is quite rigid in plant cells. So
Like bacteria also
Yes.
as a rigid one, but you're pressing more.
okay.
Rigid cell wall, okay, fine. But I'm just pressing globally on the whole thing. Rigid cell wall would be like pricking it would be more. Then you're just deforming the wall.
Okay.
But globally, if you are doing it, you will see a global response. Okay. Any doubts on
So, in the regenerative studies, if we are studying the neoblasts, so for the stem cell characterization, as in the different phases, the viscosity will be different, right?
The beta will be
Yeah.
different.
So, by that, can you characterize the stage? Like, in the metaphase, there will the
Sure.
definitely the viscosity will be different.
Along these lines, we also thought.
Yeah.
We also thought along these lines. The cell, for instance, division.
Yes.
Even division.
Yes, yes.
Cell just before cell division, when in this different G1, phases of cell. What is the beta?
Yeah.
Will be interesting question just to see what will be the value of beta for those. We are hoping that beta can become a good diagnostic tool in a say that it reports the cell's homeostasis.
Yes, so we can differentiate cancerous cells from non-cancerous.
We
With
were right
this-
now working on that.
Okay.
Okay, right now actually. Yeah. Okay. All right. So yeah.
These plots come from the microreology things.
It's a bead microreology.
Particle
in a way,
tracking.
Magnetic bead, not tracking. No.
Okay.
It's the application of stress and resultant strain. So it's still a stress strain measurement, rheology measurement.
Then there is a constraints in the.
Yeah. So that the and microreology would be different probably.
Yeah, the people are looking the power law behavior through mean square displacement.
Yes, also, and cells from that point of view is also cells do show glassy behavior.
Yes, sir.
So not just this is another interesting one. Not just macroscopic pushing and measuring strain levels. We are seeing a power law behavior, but power law constitutive equation one is using to explain MSD data, and that also fits well more than anything else.
Yeah, in some groups they collect the power law behavior from mean
Yes,
square
and then
displacement
there,
along
and
with
then there was a connection paper. I think someone in Madras has done this from what IMSC. I forgot the name, but they have put together MSD experimental data and wrote a mathematics kind of PRL, I mean kind of paper to extract out and finally establish, yes, looks like cells follow glass rheology.
Thank you.
Okay, so good. I mean, we at least one thing out of our way. We say our classification scheme now we have sort of assigned cells to soft glasses. They behave like soft glasses. Now, what good is it is the question. Now, how do one measure? And in case of AFM, one can do different kind of experiments to see this or get this exponent. The simplest protocol that you probably have already done in your labs, many of you, as we see it being talked here, is that we apply displacement to the cantilever, right? We come with the sample, press on a cantilever, come back. and this is a triangular kind of displacement that applied to the piezo, and this results when there is no contact, you do not have any force, and the force goes up like that and comes down to 0, and this is one standard protocol. So, this is basically measuring a something called a standard force curve. Okay. The second way to do that, do this particular thing is you sort of press on a cell by take the value to some to some this thing and now hold it there. So, you applied something and you hold it there and you sort of say how the force evolves. See, so, this is stressed cell now, and the stress relaxation is essentially force, it will fall down, and this falling down would be what one would like to measure as a relaxation follows a power law or no, or exponential or whatever. Third one is basically you kind of in a feedback loop hold the stress constant, and that is called creep. So, when the materials sort of keep expanding or not expanding, but keep elongating under a constant force, same you attach a weight and it is slowly going down, and that is called creep, right, we say, and then finally stops going down any further, and that kind of thing can be done with AFM by applying a force feedback, okay, which is what clamp experiment that Sabyasachi used, you have a constant force on the material, and this then will generate a creep, and that is the time required to fully elongate is the third one. This is the most common way rheology is done, okay, and probably it is also quite and when you talk to rheologists, that is what they do. Other things are not very appealing, because sometimes the creep relaxations are so fast you do not catch them. If then millisecond or microsecond, there is no, this hard to catch it. So, what is then good to do is that you provide oscillatory stress and measure the strain and see the phase lag between strain and stress, and this phase lag something called loss tangent or a tan delta that can be used to get the G prime, G double prime. Now, you do this at different frequencies. Okay. You do this from 5 hertz, 10 hertz all the way to 100 hertz, or depending on where the time scales are more relevant, go all the way up to 1 kilohertz also. And now, look at the storage modulus and loss modulus, how does it change with frequency. And if it is following a power law, it will give you something. If it is following a gel like transition, it will give you something. If it is just single relaxation time, it will give you something else. They will cross each other at one particular frequency then, and that is the relaxation time for that kind of simple materials. Okay. So, that is there are 3-4 ways in which this thing can be done, and as you can say, what is the most commercial AFMs are best suited to do this. Okay. But doing that is a problem. The problem is following. So, what do you do? What is being done is that all the protocols we looked at from, except for the first one, all of them are really nice, because we apply some constant voltage to the piezo and now see how deflection of the cantilever is relaxing, and you follow that will be like power law or whatever, or apply a constant stress and see how the creep develops in material and apply again the same power law to get whatever. But here what we are doing is you are doing constant velocity pulling or pushing. So, you go into material, you press onto a cell and you come back, and there is no way you are holding it constant and doing this. So, this way of doing things is simple because you can get more data, one thing, because creep experiments are difficult to implement, there will be a lot of other things, but this is a very nice way of doing it. And after you done this, had this been a fully elastic material like a Hookean solid we talked about, it would have been going there and coming back along the same line. Now, the reason that there is the point that there is a hysteresis in this kind of a curve means that some part is viscous, some part is not fully recovered and also not assisting you while you come back, and that is the reason why you have, for the same value of strain, you got different stress values, right. That is what the hysteresis mean, while you go and you will come back, and this hysteresis is something that is most cell mechanics data is ignoring the part which while you come back that part is ignored. We tend to fit Young's modulus or Hertzian contact mechanics, assuming it to be fully elastic solid only to the approach part and ignore the retract. And ignoring retract, basically you are throwing away a lot of information. Okay. So, and I will not go into the procedural details. This is what people normally do. You only apply Herd's model to the approach part, and this is the model. And then you know how what the Young modulus as a fit parameter one obtains. Okay, so so what one wants to do, okay, this is a bit of a context. Why is it not going further? All right, it has to wait. Okay, all right, we'll come back to that. So, from a group in Purdue University, and this is being done in many other groups also. Someone called Felix Rico in France, Ricardo Garcia, whose amplitude modulation book that you see there, and many others also are now working on a way in which you use the standard force curve, approach retract curve, and use it to obtain, and then use it to obtain by putting proper constitutive equation the information about the cell. And this is something called Ting's model. This is a paper from the Ting's paper was written, and there was a paper before that, something close to 60s, okay, mechanical engineering. And what it is telling you is that if you know, if you are deforming a material with a history, right, with a certain rate, and the time is not held constant or whatever, or the materials are not held under stress or whatever, you progressively deform and come back. How should the material behave, and those things are that equation that you see there is a Ting's equation. In that you can place your constitutive model of these as a power law or as something as a standard linear solids, which is very similar to Kelvin-Wilth. Okay. And you put in there, and then you can, this whole procedure is done for fitting the normal thing, and these are the fits using model, and this is due to a primo, and again Felix's method is similar. And you see the blue part is standard linear solids, the red part is power law rheology. Clearly the power law rheology fits better, and most important, the exponent that you obtain does not change over 3, well, at this point 1 to 10, that's at least 2 orders of magnitude. Okay. So, you are doing this fast and slow. Clearly the power law should not change, otherwise everything is problem. So, this is the first one. Then so what is the problem that we are looking at? Deepa's lab from NCCS had this curious thing that they were trying to use viscoelastic models of cell to explain this. This is one cell, and this is a transport inside a cell done through TERP microscopy. So, it is basically clathrin mediated endocytosis, and it is going nicely for a wild type cell. And now you got cells that are problematic, and problematic is that you just overexpress the Huntington's protein there, causing Huntington's aggregate, and this protein misfolds like many of these neurodegenerative diseases, and it misfolds and sits in some corner of the cell, maybe wherever it is sitting. But what it does in the process is that makes the whole dynamics of clathrin mediated endocytosis stalled completely. And from cell mechanics point of view, or whatever we learn, it is basically freezing things out. Okay. From our point of view, it is freezing things out. From biology point of view, maybe just the clathrin mediated endocytosis is not happening. Okay. All right. So, this is the behavior that they wanted to sort of understand, and then they looked at this quantification of their data. They basically look at velocities, okay, and Huntington's aggregate very low velocity, others are, and it's not only the Huntington's aggregate, they did alpha, A beta, amyloid beta, then alpha synuclein, 2 types, TDP43, FUS, all of these are sort of looked at, and only 2 of these aggregates, one is Huntington's aggregate and the other is the TDP43, only these 2 are showing this behavior of freezing things out. Okay, others you can see the transport is happening well, the velocity, the slope of these lines is kind of individual lines is velocity, right. This is basically position versus time. So, and then another curious thing is that these two cells, which is Huntington's, yeah, on the where the cursor is sitting, and also the TDP43 where the transport was sort of hindered. Both these cells are showing round shapes, whereas others are having normal philopodia. This is done again in the PAS lab and quantified this way. Okay, this is taken from this paper that appeared last year in eLife with us and Deepa. Okay, all right. So what do? We said, okay, let's take these cells and look at their mechanical response now, because fine, there's something is not right. Things
So,
are not. Yeah.
like as cells, you try to fit power law, then apply Tink's model to it. So, like for
No,
normal,
within Tink's model, we incorporate power law. Yeah.
okay. So, like for not as complex a cell, just for hydrogels, much simpler than cells.
Oh yeah, the standard linear solids works well.
Okay.
It
So,
works well.
can I just apply Tink's model directly to it without applying power law?
No, no, Tink's model is a very general thing. The constitutive equation, which happens to be the power law, you can also have standard linear solids.
Yeah.
It's your choice what you want to put in there,
Sure.
and you can do that.
Because like
Today maybe once I think the lab session you will see this,
Okay.
and Shubham will show you. You can pick up any model that you want to pick up.
So, like as for uniform hydrogels, it would be fine. But
Yeah.
if I'm like varying my stiffness or parameters, like it's a gradient gel, then
Then you do this at various parts.
Yeah.
AFM has the special resolution. You can do this with a little small size bead or even tip, and do this at different spots. Each one will give a different time scale
okay.
of relaxation, because they are not power law behavior. Gels don't follow
Sure.
power law.
They're much simpler than that.
It's just single exponent.
Yeah. Thank you.
Okay. All right. So we'll be now wrapping it up quickly. What time? Yeah.
I have this question. So, if you are fitting an SLS model, it contains two elastic components. So, where is the second elastic component coming from when we are looking at a cell? So
Elastic components, where does it come from?
yes, in a cell.
Well, the cytoskeleton is fairly elastic. The cytoskeleton just taken out of the cell and put it as a material, it is purely elastic.
So, yes, but like there are two elastic components. So, how does the components of these cells, cytoskeleton components, explains these two different spring constants?
No, see, it's not one spring. You got n number of such descriptions, and there are n number of springs with different elastic constant, and each one of these will give you one relaxation time. And what I'm saying is that the power law is basically takes, otherwise you have to take 100 standard linear solid descriptions for each process, and then or Kelvin Weig kind of a thing, and then it is the addition of each one has two parameters to fit. So if I say 11 processes happening inside a cell, 22 parameters, then nothing makes sense.
Okay, thank you.
Hello, sir.
Sir?
Yeah.
So, when we are applying force with the frequency, so does
okay, like oscillatory measurement?
yes.
Yeah.
So, is that frequency probing a certain process with a certain time scale?
Exactly. So the point is in order to do this full characterization in oscillatory way, you do one measurement and measure loss tangent, then another frequency, and like that. Now, if the system has one relaxation time scale, the two G prime and G double prime, storage and loss, will cross each other, and the inverse of that frequency is your single relaxation.
Okay.
That's the characteristic relaxation of the system.
Extrapolating that, if the forces are large,
Yeah.
can we modulate those processes individually by controlling the frequency?
By controlling the
By selecting a frequency, I'm selecting a time scale, I'm
Yes.
selecting a process, and if the forces are large enough,
Yeah.
can I modulate that process?
Oh, a priori you know what is the time scale of a certain
Yeah,
process.
prior, I know.
But that's hard one to know. That's one reason. Like for instance, inside a cell now there is kinesin walking on a microtubule. What
So
is the time scale, or what is the thing that you want to do this better with externally imposed stress or strain? That time scale is difficult to know a priori, and point is that it is also the combination of whole thing. So suppose what is thought in this business is that there is a microstructure to all materials, and each microstructure has its own relaxation time. And because there are so many microstructures, if you think of this as a continuum with each having different relaxation, the whole thing behaves like a glass.
by applying large enough force, can we modulate those processes?
I can't answer this question, because then you are saying you are applying certain frequency, you are choosing one particular process, but applying frequency just because everything is little stochastic also, right? There is no one time scale. For instance, we've seen this k on k off rates with pulling, right? And you already know that, the spread in data for single molecular interaction is coming because of stochasticity. That means even that time scale is stochastic in a way.
Yep. But if a process is happening at a specific time scale, then
Yeah,
stochastically, probabilistically, that will be preferable.
probably you can, with the large enough systems you can do that, but at a single molecule scale it's difficult to have a one time scale for one process. It's always stochastic. Putting this right here.
Okay, thank you.
So it's very difficult to, just based on time scales, very difficult to isolate or single out a system and play with it. That would be wonderful, but that is difficult inside a complex cell thing such as a cell or whatever. Yeah.
Thank you.
Okay. How are we doing on time? Maybe we already done 1 hour. Yeah. Okay, I just have 1 or 2 slides to show.
I was just curious, or maybe I've missed it, how does the beta changes in Huntington's overexpression when clathrin is stopped?
Well, come to that.
Okay, sorry.
That's what the flashpoint or anticlimax in a way. It tells how it changes. Fine. You already told us it will. Okay, the first thing to check is if I do a drug treatment such as Cyto D or Lat A, which is known to make cells softer, then the alpha probably should beta whatever. So the exponent is supposed to change, and it does change in a nice way. It becomes more liquid like. Okay, going from 0.3 to 0.4. Both Cyto D I am not showing here, but so this is comforting to know that this happens. And then this is what we did for all aggregates which showed no change in their transport behavior. Clathrin mediated endocytosis retained intact by of course wild type, and then it is alpha synuclein 2 types, beta and FUS, all of these sort of retained the transport well, and these two Huntington's and TDP43, you see now their their beta or the exponent has gone down. It has become more solid like. Essentially, in our language, it is freezing things out without changing temperature. That is. Sorry? Yeah. Yes, important process, and what it's telling you is that something has happened in the cell now, that the energy barriers have become larger to processes to happen, which means the deeper pockets now, effectively saying that it is now what really has caused this is it doesn't, we don't know what's the molecular basis for this, we don't know. Moment we then the Deepa had few ideas, and then the ways in which she could get back the transport by some treatments such as HIP1 and MRJ. So I don't know, this is Huntington interacting protein, and MRJ is something else. But these they showed that the transport can be restored back. It's called rescue experiment in biology. And once they can do that, then we said, wow, go, great, give us those cells, and we measured the beta once again on them, and you see beta is also restored back. So it's there that the homeostasis of the cell, as long as it is kind of functioning well, it will have a beta in the range of 0.3, 0.4. This also one should know. Suddenly you start getting all these procedures start getting a value of 0.8, then it's really hard thing. It's not really measurement of Young's modulus, but it's really beta is something that is we are thinking could be a nice way to sort of figure out the some diagnostic aspect. The cell is fine and nice and everything great about it. Maybe you will have beta that's hovering around 0.3, 0.4. But moment there is a problem, it could go either way. It could go either way. So that is what we are now trying to explore with other cells, with Nagaraj's lab, and similar behavior we are seeing on another cell. And this is what someone asked, cancer cells we are going to take the next year. Sorry? That's the exponent. Sorry, the alpha and beta is one and same. Yeah, I somehow you should put beta there because the initial discussion I'm saying alpha and then beta and then saying alpha.
Sir, the spreads in the box plot, do they also tell us something about the cells themselves, like heterogeneity or whatever?
Yeah, it will. We haven't looked at them carefully, but you can, yeah, in case of clearly getting the E0, it's called instantaneous, or just like J0 in the previous one. So that one shows a larger spread. We haven't looked at that carefully, but
okay, but that could also be useful information.
Could be useful, yeah. Spread in the data.
Sir, that alpha represents the power law behavior. So
yes, the exponent of
the exponent. Yeah. So it's between 0 and 1. It says about the viscoelastic natures.
Between 0 and 1, it always has to be between 0 and 1. As I say, the fractional calculus thing, it cannot take, because this full liquid like is 1, full solid like is 0, and nothing is beyond Hookean solid and beyond Newtonian liquid, there is nothing. So it has to be bound by 0 and 1.
We can take that alpha value particular regions, or we can take into 2 segment regions to define the power law behavior.
Oh, how much is this part frozen out compared to the other part?
Yeah, because once you mention the last tangents,
yes,
that's come from the G double prime over the G prime.
That's possible. We haven't tried making local measurements. All these measurements are done with pressing on the cell fully, I mean globally, not just locally, because the cells are about 5 microns and the bead size also
the comparable to
that.
Thank you, sir.
Yeah. Then the left hand side. Oh, the number of measurements that is written in the paper, I think runs into hundreds of thousands, lot of them.
And so normally you just plot the mean value per cell.
Yeah, after fitting, each measurement is fitted separately, and then it is over different cell. With each type of cell, 15 cells are sort of looked at. Each cell, couple of hundred, and then we do analysis separately on each cell and see, and then if there are heterogeneities that we can see. But if there are no heterogeneities, then we put all together and get a standard error.
Yeah, because I was also asking, because if you have flatter cells,
yeah,
close to the nucleus, the stiffness is normally higher. So would the beta then vary depending on the region as well, or is it?
Might, but then you do that with a tip.
Okay.
I mean, to begin with, we went away from tip because we are saying that in order to say that all time scales are probed, all regions of the cells probably should be probed. And that's what gives it power law behavior. If I poke little at one place, maybe it's not a power law. It will probably just give you some time scales.
So this is with beat?
This is beat, yeah.
Okay, thank you.
Following up that question, what beat size you would suggest for this kind of microradiology?
Depends on cell size.
Okay.
So roughly here we take the cell and bead size to be same.
Okay.
And our cells are something like 5 microns.
Okay, 5 microns.
But if you take a neuronal cell, then you, on a philopodia, you probably can they are much bigger. And then there is no way to get away from locally pressing, which is also okay. I don't see much of a problem.
Getting
Because with the
global,
bead also we pressed on organisms to get, like we did this Hydra work, and that tissue is somehow fully elastic. I told my students, if there is a hysteresis in the curve, no way. So we then could only use Young's modulus description, which is the Hertzian description. So on tissue, if you do many times on tissue, you do not see power law. It's the recovery is full.
so it's Hertzian.
Hertzian.
Wow.
I don't know the reason why, but it is what seems to be the case. So if you take a epithelial whatever confluent layer or something and you try doing this, maybe it's likely that you will not see all of this power law behavior.
Maybe it's stacking up.
Maybe it's bulk material now, I guess. And then there is boundary of each cell, like grain boundaries in a mechanics. All of that could be the reason. Yeah.
Thank you.
So, can you please talk about how the cells were adhered to the whatever substrate while doing like some experimental?
This was done with extremely. One thing that's a very, very important question. What you would like to do is keep the substrate extremely high in terms of Young's modulus. So you take like gels of the order of few kilopascals, and the cell and gel is similar stiffness, and you press on them, both of them get pressed, and you don't know whose response you are measuring. So we take glass, and then for Nagaraj's work we have a collagen, which is extremely thin layer of collagen with polylysine and things, so that the cells are nicely sitting there without spreading too much. And in case of Deepa's work, we use, I think, some other gel. I forgot now which one.
So
but then what we did was make a measurement on just that gel, and it should be cross-linked with enough concentration so that when you press on it, it should give you at least some 100 megapascal or so Young's modulus. So when you're pressing on a cell, you're not really pressing, the gel is not getting compressed. That is
So you said the bead size is 5 microns, right? The cell size is comparable, as in it is around the same. So when you are fixing the cells on the substrate, basically the bottom part is stuck to the substrate, right? So does that not affect the measurements? Because no, I'm just trying to understand, do we need the cell to be a little detached from the substrate? Like for example, when
if you have a cell detached from the substrate, you press on it, then it moves with it. It doesn't
as
get
in
deformed.
there are people when they do experiments where the cell is localized between two beads. So why do they do that exactly? Because they say they need the cells a little, not completely fixed to the cell. That is why they're using these two beads to just kind of lift the
surface
cell.
in our case is just the other bead, because you have to squeeze them somehow between two rigid surfaces. Then only you can deform them,
right?
And there's a stress imposed,
right.
And that's when you make mechanical measurement.
Okay.
So if they want to keep it away from substrate, fully flat substrate, and then put them between the two beads. I don't know which experiment you're talking about really, but it's basically the optical tweezer. If this is optical tweezer measurement,
it was a pulling experiment, so maybe that is different from.
And it's a different pulling is different, and it can two spheres, let's say, of 1 micron diameter, when they put in contact with each other, depending on the force by which you are pushing, Hertzian mechanics will tell you what is the contact area, and this will, depending on the Young's modulus of the material and the force, that's what Hertz mechanics is, decides what the contact area is. Typically it will range up to 1 to 10 nanometer square for 1 micron bead.
Right.
And that's where single molecule interactions are possible with a bead that is as large as a micron, because the contact area is that small. Now if you have a cell pressed between two beads which are micron or so, the cell is much bigger and the beads are smaller, and you're squeezing, but you're squeezing locally once again.
Right.
So you have to like 10 micron, 50 micron beads, but they're not colloidal anymore. They're harder to hold there, they will fall under gravity. So or whatever the
So
band
it's an
mass is.
optimized
So
size
it's
between.
yeah. So that is for good for single molecule thing. I
Mm.
think tweezer explains.
Thank you.
Also the force sensitivity. Applying a force of 1 nanometer to the tweezer is a little hard.